Okay, so you've seen your test grade and you're either happy with it or you're unhappy with it. And I just want to encourage you or to tell you this is a very, very, very early in the semester. It's the first test. And so we've got several more tests that will keep averaging and change your average. So this is going to be 2.5 through 2.8. Some similarities to the first section and then some new stuff too. So are we ready? Are you listening? Got your ears up? The fundamental theorem of algebra, section 2.5. Fundamental theorem of algebra says if f of x is a polynomial of degree n, where n's greater than 0, so n's a positive, so the degree of our polynomial is a positive value, then f has at least one 0 in the complex number system. So if f of x is x to the fourth plus 2x, our degree is 4, that's greater than 0. So this theorem guarantees that we have at least one 0, at least one complex 0. But you remember how we could write any number as a complex number? Even 8 could be a complex number because it would be 8 plus 0i. So it's not the most amazing theorem in the world, but I needed to show it to you. Next is the linear factorization theorem. If f of x is a polynomial function of degree n, again, n's greater than 0, this one is nice. Then f has precisely n linear factors. So if you have this polynomial, let's say we had this. That's our polynomial. Our degree is 4. So this says as long as that 4 is greater than 0, which it is, then we have precisely, exactly n linear factors. So we have 4 linear factors. Linear, that sounds fancy, but it's just in this y equals mx plus b form, so it's just an x minus a constant, a linear factor, or just an x, because that could be written as x minus 0. So that's all this is saying right here. We might have some coefficient here, and then it's just like x minus 5, x minus 2, and so on until you get to x minus 8 or whatever. So it's just, we can break down our function to sets of factors. And how many factors we would have would be exactly equal, precisely equal to our degree. So it's kind of a complicated way to say it, but let's go ahead and start with example 1. So go ahead and look in the book with me on page 135. Okay, so example 1. The first degree polynomial, f of x equals x minus 2, first degree because the highest power of the x is a 1, has exactly, according to that linear factorization theorem, has exactly 1 0, which is x equals 2. And that's its only factor, too. It could be written like this. Linear factorization theorem has that factor right there. By B part, counting multiplicity, the second degree polynomial, f of x equals x squared minus 6x plus 9, degree of 2 right here, second degree, would have exactly 2 zeros. Let's factor it. They're both x equal 3. But since multiplicity counts, and there's 2 of those, then those are our 2 zeros. They're exactly the same. Okay, this third degree polynomial function, because the highest degree is a 3, should be 3 zeros. So let's see what they are. Let's take our function and let's factor it by taking out an x.
That was not good. He was like, I saw that. And I was like, no.
Now, x squared plus 4 doesn't factor again, so you're going to set both of these factors equal to 0. So x equals 0, that's done. That's one of our zeros. And x squared plus 4 equals 0. So we can solve this. We'll minus 4 on both sides. Take the square root of both sides. And that's a perfect square, and it's negative, so it's plus or minus 2i. So we got a 0 of 0, and we have a positive 2i and a negative 2i for exactly 3 zeros. So the fourth degree polynomial function, x to the fourth minus 1, fourth degree, because of that, we'll have exactly 4 zeros, and let's find them. Let's set this function equal to 0 and solve it by factoring. So this is a difference of squares. X squared minus 1, x squared plus 1. This x squared minus 1 is going to factor again as another difference of squares. X squared plus 1 just gets brought down. So that's as far as they'll factor. Now you set each of your factors equal to 0. X plus 1 equals 0, and you get your negative 1. X squared plus 1 equals 0, minus your 1. Take your square root of your negative 1, and that is by definition I. So our 4 zeros are 1, negative 1, I, and negative I. Exactly 4. Okay, example 2. We're going to confirm that the third degree polynomial function, f of x equals x to the third plus 4x squared plus 9x plus 36 has exactly 3 zeros. And we're going to confirm that by solving it, trying to find the zeros. So we look at this, and there is no GCF, and there's 4 terms. And before Christmas, we talked about how to factor 4 terms. One way was to group it in groups of 2. So if we try to factor by grouping, we can factor out x squared in the first group, and we can factor out a 9 in the second group. And then the x plus 4's match, so we can factor the x plus 4 out, and you're left with x squared plus 9. And now when you look at these two factors, neither of them factor more. So we're done factoring. We're ready to just set our factors equal to 0 and find our zeros. So we get negative 4 for one of them, minus 9, and you're probably getting used to how this type of factor is going to work. Take the square root of both sides. So it's plus or minus 3i. And those are your 3 zeros. You have the zeros negative 4, 3i, and negative 3i. All right, example 3, we're going to write this fifth degree as a product of linear factors and list all the zeros of f. And we should come up with 5. And we should have 5 linear factors. We do not have a way to factor 5 terms, and this thing doesn't have a GCF. So we're going to have to use the rational zero test on it. So we have 8 over 1. So our possible rational zeros are these. And then we can check on our calculator for which ones are going to work. And it looks like 1 will work. So let's do synthetic division with the 1. So we got 1, put a 0 for x to the 4th, 1, 2, negative 12, and 8. Just writing down all of our coefficients. 1 times 2 is 2, is 4, 4, negative 8. Oh, it's looking good. So there's 1 0. But this is still too large to try to factor. And so if we look at our calculator for another intercept, it looks like negative 2 is an x-intercept. So let's use it. Just running through the synthetic division. Ooh, got another one. And now this one is okay to factor because that's our remainder, our constant. Oh, no, it's still too big. It's not an x squared, but I do think this one is going to factor just by the pattern I see. So let's write it down. We got 1x cubed minus x squared plus 4x minus 4 equals 0. That is going to factor by grouping. Take out the GCF of the first group. Take out the GCF of the second group. And they match. So write down the part that matches, and then write down what's left once you factor that out. And you've got this factor, which gives you this 0. And you have this factor, which if you've noticed how that pattern is working, it's going to give you this 0. But the reason why, if you haven't noticed it yet, is we'll minus 4 on both sides. And then we'll take the square root. So x is plus or minus 2i. It wants us to list all the, write it as a product of linear factors. I'm going to erase my p over q. So my product of linear factors is, let's write the zeros first. With synthetic division, we got this one and this one. And then by factoring, we got this one and these two down here. So then to write them as the linear factors, it's x minus 1, x plus 2, just an x. This is just an x, and usually we'll put that in the front. And then you have x minus 2i and x plus 2i. But they won't actually like that, the 2 i's. And they would rather us say x minus 1, x plus 2, and then x minus 2i would have been x minus the square root of negative 4. And x plus 2i would have been x plus the square root of negative 4. Okay, so please ask me about that on Thursday if that doesn't quite make sense. Your homework for tonight will be, right, 9 through 12 all and 17 through 35 odd. Somewhere around 20 problems. And most of them, or a lot of them, let's see, let's just take out 9 through 12 all. And let's just do 17 through 35 odd. Alrighty, good luck.